A white expanse stretches beyond the horizon, unbroken, infinite. The wind whispers across the ice in a soundless language, carrying with it the chill of a world that has never known warmth. Here, in Antarctica, the Earth feels alien, a place both profoundly familiar and utterly different. The silence is not merely absence of sound, but a presence itself, a void so complete that it mirrors the emptiness of space, a cold so absolute that it reminds the mind of distant planets, untouched and waiting, under the pale glimmer of a sun that barely rises above the horizon. The ice reflects a perfection of stillness, a frozen eternity that seems to stretch beyond the confines of time. The landscape is more desolate than the driest deserts, colder than the most forbidding reaches of Mars, and more isolated than the far side of the moon. Each snowdrift, each frozen ridge, whispers a story of survival against odds so extreme they seem almost cosmic. It is here, at the edge of the Earth, that humanity confronts the paradox of life, fragile, fleeting, yet stubbornly persistent. Antarctica is no ordinary continent. It is a laboratory written in ice, a mirror of worlds beyond our own. Beneath its frozen surface, secrets of the cosmos lie preserved in layers of ice, waiting for those willing to endure the merciless cold. Microbial life, hidden in subglacial lakes, survives in conditions that seem impossible, hinting at the resilience of life in the universe. Meteorites, fragments of distant worlds, rest on the icy plains, telling silent tales of interstellar journeys that predate human memory. The continent becomes a bridge between Earth and the stars, between known life and the possibility of life elsewhere. To stand here is to stand at the boundary of human understanding, to face the limits of endurance and perception. Every breath, every step, is a testament to the delicate flame of life amid overwhelming cold. In the stillness, one begins to sense the subtle rhythm of the universe, the invisible threads that connect ice and cosmos, earth and sky, the present and the infinite. It is a place that invites contemplation, that demands reflection. The mystery emerges gradually, like the pale glow of the Antarctic dawn. Why does studying this frozen wasteland bring us closer to comprehending the vastness of space? How can the survival of microbes beneath kilometers of ice illuminate the potential for life on other worlds? Antarctica is both mirror and teacher, revealing truths not through spectacle, but through quiet persistence, through conditions that test the very essence of existence. Humanity, warm-blooded and fragile, ventures here not merely to endure, but to understand, to glimpse the possibilities that lie beyond the confines of Earth, to touch, if only fleetingly, the edge of the cosmos here, at the limit of endurance. Amid ice that stretches like a pale ocean, the journey begins, a journey not just across a continent, but into the heart of a mystery that binds Earth to the stars. Long before the world understood the silent lessons Antarctica held, men and women ventured into its frozen embrace, drawn by a mixture of curiosity, ambition, and the fragile hope of discovery. Shackleton, Scott Amundsen, names now etched into the annals of exploration, moved across a landscape that seemed almost designed to resist human presence. Each step was a negotiation with a planet made of ice, each breath a confrontation with a cold that seeped into the bones, a cold that no fire could fully erase. Their journeys were not just physical trials, but philosophical confrontations with the extremities of existence itself. The continent revealed its contradictions immediately. On the surface, it was an unbroken expanse of white, yet beneath lay secrets that would challenge the very understanding of life, survival, and the cosmos. Scientists observing these explorers soon began to recognize Antarctica not merely as the southernmost edge of Earth, but as the coldest, driest, and most inhospitable place known to humanity. Temperatures plummeting beyond imagination. Air so thin and dry it mirrored conditions on Mars. The ice sheets stretching like alien oceans under a sun that barely warmed the ground. Here was a world that seemed to exist in parallel with the planets beyond our sky. It was in this desolation that a subtle connection emerged between Earth and the cosmos. Early researchers began to see the parallels. Subglacial lakes, isolated for millions of years, hinted at the possibility of life in similarly hidden reservoirs on other worlds. Dry valleys, barren and sterile, offered a glimpse into the challenges that life might face on distant planets. Even before the first spacecraft had left Earth's orbit, Antarctica was providing humanity with a terrestrial rehearsal for extraterrestrial exploration, a laboratory where survival, adaptation, and discovery could be studied under conditions that bordered on the impossible. Among the first profound cosmic hints were the meteorites scattered across the icy plains. Preserved in the frozen silence, fragments of Mars, asteroids, and perhaps even the earliest remnants of the solar system rested undisturbed for millennia. These silent emissaries of distant worlds sparked both scientific and philosophical wonder. Here, on the coldest continent, lay a bridge between Earth and the stars. Each discovery suggested that the ice was not merely a barrier but a repository, a keeper of cosmic history, patiently awaiting the eyes and minds capable of reading its frozen script. In this crucible of extremity, humanity first began to understand its own fragility and its potential for endurance. Antarctica was no longer merely a geographic end. It became a symbolic threshold, the edge of known experience, where every struggle, every observation, hinted at a larger journey beyond the planet. It was here, in the relentless cold and blinding white, that the first whispers of the universe's secrets could be heard, suggesting that the search for life, for meaning, and for connection to the cosmos would begin not in orbit, but on the ice. The continent, silent and eternal, offered its lessons in patience and persistence. Every frostbitten ridge, every meteorite waiting beneath the ice, was a reminder that understanding the universe required endurance, curiosity, and the courage to confront environments that challenged the very essence of life. Antarctica, in its alien stillness, was humanity's first rehearsal for stepping into the void beyond Earth, a proving ground where the echoes of the cosmos could be felt in the cold wind that swept endlessly across the ice. As explorers pressed deeper into the continent's heart, their experiences began to shape the first scientific understanding of Antarctica's extremes. Scott's Terra Nova expedition meticulously recorded temperatures that defied comprehension, measuring winds that could strip flesh from bone, and documenting the subtle ways the ice shifted and groaned, as though the continent itself were alive with slow, inexorable motion. Amundsen's careful navigation of the polar plateau revealed an elegance in the landscape, a geometry of glaciers and snowfields that reflected light with a brilliance that seemed almost otherworldly. Each measurement, each journal entry, became more than a record. It became testimony to the extraordinary capacity of life to confront inhospitable conditions. Early observations by these pioneers hinted at a world that was both delicate and resilient, a paradox that would later resonate through astrobiology. The cold, for example, was not merely destructive. Beneath the crushing temperatures, the ice preserved ancient atmospheres, frozen microbial life, and, eventually, the meteorites that would provide humanity with its first tangible connections to other worlds. In these frozen layers lay the potential to reconstruct the history of the solar system, to trace cosmic events that predated human civilization. Antarctica was becoming a natural archive, a repository of planetary memory, offering a glimpse of the universe not in distant light, but in tangible fragments embedded in ice, Scientists soon began to recognize patterns that mirrored extraterrestrial environments. The McMurdo Dry Valleys, an expanse where liquid water is almost non-existent, provided the first real-world analogue for Martian terrain. Researchers observed how life, in the form of microbial mats, survived against the odds, drawing sustenance from minimal moisture and the rare sunlight that penetrated the harsh skies. The idea that life could persist in such extremes began to shift humanity's understanding of what was biologically possible. If organisms could endure in the frigid, arid isolation of Antarctica, could similar forms survive on a world like Mars, buried beneath frozen regolith, waiting for the faintest spark of energy? Meteorites, scattered and waiting upon the icy plains, reinforced the continent's cosmic significance. Unlike any other place on Earth, the ice acted as a natural collector, concentrating fragments of Mars, the Moon, and asteroids in fields that were easily visible against the stark whiteness. Scientists recognized that these fragments, some millions or even billions of years old, offered an unprecedented opportunity to study the material of other worlds. Without ever leaving Earth, each piece was a silent messenger, its surface scarred by eons of travel through space, whispering secrets of planetary formation, chemical evolution, and the possibility of life elsewhere. Antarctica, in this sense, was not merely Earth's southernmost continent, it was a cosmic observatory, a place where the story of the universe could be read in ice and stone. The philosophical implications of these discoveries were as profound as the scientific ones. Antarctica became a space of contemplation, where the limits of human endurance mirrored the limits of our understanding. To walk across its endless plains was to confront both mortality and the infinite, to feel the fragility of the body against the indifference of the environment. Every expedition revealed not just the extremity of the ice, but the resilience of life, the stubborn persistence of curiosity, and the human capacity for wonder. Shackleton, Scott, and Amundsen had been adventurers, yet, in retrospect, they were also the first astronauts, navigating an alien world with no safety net, charting unknown territory not unlike the explorers who would centuries later journey to Mars or the moons of Jupiter. By the early 20th century, scientists began to formalize Antarctica's role as a model for space environments. Laboratory experiments and observational studies drew on the extreme cold, dryness, and isolation to simulate conditions that spacecraft and future planetary habitats would face. Researchers considered how instruments might withstand sub-zero temperatures, how humans might cope with sensory deprivation, and how life could be sustained in sealed, self-contained ecosystems. Antarctica had become a proving ground, a rehearsal for humanity's ventures into the cosmos, where every logistical challenge, every survival strategy, and every observation offered a lesson for the broader universe. Even now, the earliest meteorite finds carry an almost mystical significance. Each fragment preserved in Antarctic ice is a bridge across time and space, a relic of collisions that shaped planets, perhaps even carrying the chemical seeds of life. These discoveries suggested a continuity between Earth and the wider solar system, a notion that would influence generations of planetary scientists. The ice, silent and immutable, became a canvas on which humanity could project its questions about origins, life, and the cosmos. The lessons learned here were not abstract. They were tangible, rooted in the frozen terrain, in the endurance of explorers, and in the microscopic traces of life that persisted against unimaginable odds. Antarctica, in its stark isolation, demanded reflection. It asked those who ventured into its whiteness to confront the limits of knowledge, to accept uncertainty, and to find meaning in persistence and observation. Each expedition, each measurement, each meteorite discovery built a cumulative understanding. The extremes of this continent mirrored the extremes of space, and the study of one illuminated the other. Humanity, fragile and warm-blooded, stood at the threshold of understanding, realizing that Earth's final frontier was not merely a geographic boundary, but a conceptual bridge to the stars. In the silence of ice and wind, the first whispers of the universe's larger mysteries could be discerned, guiding the mind toward the realization that the pursuit of knowledge, like life itself, often thrives in the harshest, most unforgiving of places. For decades after the heroic age of exploration, Antarctica remained a curiosity more than a frontier. Early scientific observers regarded it as a frozen curiosity, a place of extreme weather patterns, shifting ice sheets, and geological anomalies, fascinating but largely irrelevant to the grand narratives of biology or cosmic inquiry. Maps were drawn, meteorological readings taken, and yet the continent's deeper potential remained largely unconsidered. To most, it was simply the end of the world, a terminus of human habitation, and a laboratory too remote to justify serious investment. Yet beneath the initial dismissal, subtle patterns began to emerge, slowly reshaping scientific imagination. Researchers noted that the extremity of Antarctic conditions mirrored, in some ways, the alien worlds that humanity could only dream of visiting. The thin, dry air of the McMurdo dry valleys, the relentless cold of the polar plateau, the crushing isolation of subglacial lakes. These were not merely harsh landscapes on Earth, but terrestrial analogues for Martian plains and the hidden oceans of icy moons. The realization was quiet at first. To survive here was to survive in environments that approached the limits of life itself, a rehearsal for the challenges of the cosmos. Astrobiology, still in its infancy, began to find its first footholds amid the ice. Researchers discovered microbial life, enduring in veins of frozen water and briny pockets beneath kilometers of ice, thriving in darkness and starvation. These organisms were unlike any seen before. Their metabolic processes adapted to extreme desiccation, near absolute zero temperatures, and complete isolation. The ice itself became a mirror of possibilities. If life could persist here, could it exist on Mars, beneath its regolith, or within the hidden oceans of Europa and in each new sample, each carefully catalogued microorganism, whispered hints of universality, of survival against cosmic odds. The emotional impact of standing on this frozen continent was immediate and profound. Scientists often described a sensation of being simultaneously infinitesimal and yet deeply connected to the universe. To walk across an ice sheet, under skies that seemed impossibly vast and empty, was to feel the raw essence of life stripped to its core. Every gust of wind, every creak of the glacier, reminded observers of fragility and resilience intertwined, the human body and mind confronting the same extremes that had tested life for millennia. The cold was no mere environmental variable. It was a teacher, a harsh mentor instructing humanity in endurance, patience, and awe. Gradually, the narrative shifted. Antarctica was no longer simply a geological or climatological curiosity. It became a stage upon which Earth and space converged. Meteorites, preserved in the ice for eons, provided the first tangible connections to other worlds. Fragments of Mars and the asteroid belt lying undisturbed until human eyes arrived. The ice itself, layered like a ledger of millennia, recorded atmospheric shifts, cosmic impacts, and the slow march of time, offering lessons for planetary science and climate models alike. Scientists began to see that the continent's extremity was not an obstacle, but a tool, a natural laboratory for understanding conditions that would be encountered beyond Earth this dawning. Realization brought with it a philosophical weight. Antarctica was not simply a place to study. It was a crucible, a site where life and non-life, human endurance and cosmic history intersected. Standing there, one could not escape the reflection that the planet's extremes were a rehearsal, a mirror for humanity's aspirations beyond its cradle. Survival in Antarctica was survival in miniature, a test of adaptation, innovation, and resilience that hinted at the broader questions of life in the universe. It was here, in the austere whiteness, that the earliest inklings of humanity's cosmic consciousness began to take shape. The ice and the microbes, the meteorites and the wind, all converged into a single lesson. Understanding Earth's extremes was inseparable from understanding life itself, and, by extension, the possibilities of life elsewhere. Antarctica became the quiet stage upon which science and imagination could meet, where cautious observation intertwined with daring speculation, and where the awe of discovery was inseparable from the humility of survival. The first scientific reactions, once dismissive and skeptical, had transformed into reverent attention, laying the foundation for decades of research that would reveal Antarctica not merely as a remote continent, but as a gateway to understanding the cosmos. As the initial awe settled into systematic inquiry, the continent revealed subtler, more profound lessons that could not be captured in simple measurements or charts. The ice sheets themselves, stretching endlessly in every direction, became a medium for discovery. Layers upon layers of compressed snow preserved atmospheric traces from hundreds of thousands of years ago. Tiny pockets of air trapped in crystalline matrices, each a frozen sample of Earth's evolving climate. Scientists realized that by drilling deep into these layers, they could reconstruct not only the history of their own planet, but also the chemical conditions that might exist on other worlds. The parallels were striking. Understanding the composition of ancient air in Antarctica offered a framework for interpreting the atmospheres of Mars, Venus, or exoplanets light years away. Even the smallest discoveries carried profound implications. Lichen, resilient mosses, and microbial mats, found clinging to rocks in the seemingly lifeless dry valleys, demonstrated that life could persist without warmth, without abundant water, and with minimal nutrients. Researchers began to imagine how such organisms might survive beneath the surface of ice-covered planets, protected from radiation, yet thriving in niches invisible to the naked eye. These life forms were not just biological curiosities. They were living proof that the universe could harbor resilience, that the constraints of environment did not necessarily dictate the impossibility of life. In this way, Antarctica became both a mirror and a laboratory for astrobiology, a tangible reference for conditions previously considered purely theoretical. Meteorites, meanwhile, accumulated like fragments of an interstellar puzzle across the frozen plains. Scientists initially stumbled upon them by chance, but soon systematic searches revealed thousands of specimens, each bearing chemical signatures of other worlds. Some originated from Mars, others from the asteroid belt, their surfaces etched by cosmic radiation during journeys lasting millions of years. The ice acted as both protector and amplifier. By preserving these objects in stark contrast against a featureless white landscape, it allowed them to be discovered with remarkable efficiency. The implications were staggering. Antarctica was not merely a recipient of cosmic debris. It was a lens into planetary history, offering direct access to materials formed in environments unreachable by human hands. As more scientists ventured south, the emotional resonance of the environment became inseparable from the intellectual discoveries. Standing beneath the polar sky, observing the sun grazing the horizon with an almost imperceptible motion, researchers reported sensations that transcended conventional scientific measurement. The ice, endless and immaculate, imposed both humility and introspection. Every experiment, every sample collected, carried the weight of human fragility against the stark eternity of this frozen world. It was an environment that demanded respect, that imposed patience and endurance, teaching a lesson as profound as any data set, that understanding the cosmos required not only intellect, but immersion, endurance, and the willingness to confront extremes. Philosophers and scientists alike began to draw connections that extended beyond practical research. Antarctica became a symbolic threshold, a place where the limits of life, endurance, and understanding could be explored in miniature, before humanity attempted similar challenges on other planets. The continent's extremity forced a reckoning with the nature of survival itself. If life could persist in the sub-zero isolation of a subglacial lake, if organisms could endure millennia trapped in ice, then the conditions necessary for life elsewhere might be less restrictive than previously imagined. Antarctica was teaching that the universe, while vast and indifferent, might still be hospitable to persistence, adaptation, and resilience. By the mid-20th century, a quiet transformation in perspective had taken root. Scientists who once considered the continent's relevance marginal now recognized its unparalleled value. Antarctic research stations, initially temporary outposts, became permanent laboratories, allowing sustained observation of both the environment and the human response to its extremes. Psychological studies, for example, revealed how isolation, extreme cold, and sensory monotony affected cognition and morale, insights directly applicable to long-duration space missions. The continent was no longer a mere curiosity. It had become a crucible for understanding not only life on Earth, but life in the universe. The merging of ecological, geological, and cosmic observations created a narrative that was at once scientific and philosophical. Antarctica, it seemed, existed at the intersection of extremes, a place where the tiniest microbial organism could endure, where frozen fragments of other worlds could lie undisturbed for eons, and where human beings could confront their own limitations. The continent's lessons were profound. Survival, adaptation, and curiosity were inseparable. Knowledge emerged not in comfort, but at the edges of endurance. Each expedition reinforced the idea that Earth's most desolate places could illuminate the conditions of worlds far beyond our atmosphere, and that the study of these extremes was inseparable from the pursuit of cosmic sought understanding. In the silence of the polar night, when wind howled across empty ice plains and the sky glimmered with stars unseen from most of the planet, early scientists and explorers began to perceive something deeper than meteorites, microbes, or climate data. They sensed the rhythm of a universe mirrored in the frozen earth below their feet. Antarctica had ceased to be simply a location on a map. It had become a philosophical and scientific threshold, a rehearsal stage for the human imagination, a place where the conditions of survival, resilience, and discovery converged. The first scientific reactions, once hesitant and dismissive, had evolved into reverent attention, and the ice whispered an unspoken promise that understanding the extremes of Earth was inseparable from glimpsing the possibilities of the universe. Beyond, as the mid-20th century unfolded, Antarctica shifted from a landscape of heroic exploration into a deliberate laboratory, a place where human ingenuity confronted extremity with intention. Permanent research stations began to pierce the horizon, humble clusters of steel and fiberglass that braved wind, snow, and isolation. These outposts were more than mere shelters. They were laboratories at the edge of survival, crafted to withstand temperatures that fell below -80 degrees Celsius, where blizzards could last for days and the sun could vanish for months. Within their walls, instruments hummed quietly, measuring everything from cosmic rays to the chemical composition of ancient ice, while human occupants learned to live with scarcity, monotony, and unrelenting cold. The people stationed here became subjects as well as observers. Researchers noticed that human endurance in isolation, limited sunlight, and extreme cold mirrored the physiological and psychological challenges astronauts would later face on months-long space missions. Cognitive studies revealed subtle changes in perception, circadian rhythm disruptions, and the slow accumulation of fatigue, offering a terrestrial glimpse into the effects of living in an environment where nature itself resisted human presence. Survival here was not merely a test of equipment or scientific methodology. It was a test of resilience, patience, and adaptability. Each day in the polar night, each measured heartbeat against the icy silence, became an experiment in endurance, teaching lessons that extended far beyond the bounds of Earth. Simultaneously, the first true analog experiments began. Drilling ice cores became a ritualized practice, one that resembled the methods scientists would later employ in planetary exploration. Cylinders of ice, some thousands of years old, were carefully extracted, catalogued, and studied for their physical, chemical, and biological properties. Each layer was a frozen page of Earth's history, recording atmospheric composition, volcanic activity, and the subtle imprints of cosmic dust. The act of drilling, of reaching deep into the frozen crust, was simultaneously literal and metaphorical humanity, reaching down into the past to prepare for future encounters with alien worlds. The parallels were unmistakable. Just as explorers probed the ice, space missions would probe the frozen regolith of Mars, the permafrost of Europa, and the icy moons of the outer planets, seeking the same clues to planetary history and the existence of life beneath the ice, in lakes that had been sealed from the atmosphere for millions of years. Scientists discovered microbial communities thriving in darkness and near-freezing temperatures. These organisms, shielded from radiation and sustained by chemical energy, offered a tantalizing window into the possibilities of extraterrestrial life. Subglacial lakes such as Vostok and Willans became analogues for the oceans thought to exist beneath the icy crusts of Europa and offering a glimpse of how life might endure in environments that seem inhospitable to humans yet are fertile in their hidden complexity. Each microbial colony became a small, resilient proof of concept. If life could endure here, it might endure elsewhere. The frozen plains also became a canvas for cosmic archaeology. Meteorite hunting intensified, with researchers scouring the ice for fragments that had traversed the solar system for millions of years. Antarctica's ice acted as a natural collector, concentrating spaceborne rocks into fields where they could be identified with relative ease. Each meteorite was a time capsule, a fragment of a world far removed from Earth, carrying within it the chemical signatures of its birthplace. For scientists, these pieces provided more than raw data. They were tangible connections between Earth and the cosmos, allowing a direct dialogue with worlds otherwise unreachable. Antarctica had become, in essence, a proxy universe, a miniature cosmos preserved in ice, where earthbound observers could investigate the processes and materials of distant planets without leaving the planet itself. This convergence of biology, geology, and astronomy began to shift perception once again. Antarctica was no longer simply extreme, it was exemplary. It had become a crucible for testing ideas, hypotheses, and endurance, a place where each experiment could illuminate broader truths about life, survival, and the conditions necessary for both. The continent's extremity revealed patterns, relationships, and limits, creating a framework for understanding environments far beyond the familiar blue sky of temperate regions. Scientists began to see it not as an isolated anomaly, but as a critical lens through which the universe could be examined, a stage where the extremes of Earth mirrored the extremes of the cosmos. In the silent stretches of ice and the depths of hidden lakes, Antarctica whispered its lessons to those willing to listen. Each drilled core, each microbial sample, each recovered meteorite contributed to a growing realization. This frozen continent was more than a laboratory. It was a rehearsal space for humanity's cosmic ambitions, a place where survival, observation, and imagination intertwined. Here, at the edge of endurance, Earth itself became a proxy for the universe, offering a glimpse of life, history, and resilience in conditions that challenged both body and mind. And in that frozen, luminous stillness, the journey of discovery deepened, revealing that the mysteries of space were often mirrored in the extremes of our own world, waiting patiently beneath layers of ice that spanned millennia. As research stations solidified their presence across the continent, the scope of investigations broadened, moving beyond human endurance and ice core analysis into experiments that probed the very limits of Earth and life. Instruments were calibrated to measure subtle vibrations in the ice, the shifting of glaciers, and the quiet accumulation of cosmic dust falling from the sky. Scientists began to recognize that Antarctica was not merely a place to record data, but a dynamic laboratory where the Earth itself revealed processes otherwise invisible in more temperate regions. The ice sheets were living archives, their structure and movement chronicling climatic events, tectonic shifts, and even impacts from distant celestial bodies. Each observation became a lesson in scale, in patience, in temporality, and in the delicate interconnection between Earth and the cosmos. The human dimension of these studies also intensified. Researchers stationed in the interior faced months of darkness, where the sun did not rise for weeks, and sensory monotony challenged perception and resolve. Psychological studies documented the subtle effects of isolation, where the mind, deprived of normal social and environmental cues, adapted in unexpected ways. Sleep cycles lengthened and shortened unpredictably, cognitive focus fluctuated, and yet innovation persisted. Habits and routines became acts of survival and observation simultaneously. In this way, Antarctica provided a preview of the human experience in deep space, confined quarters, extreme conditions, and the necessity of maintaining function and focus despite environmental hostility. Each expedition contributed not only scientific data but also insights into the adaptability of consciousness itself. Meteorite collection evolved into a rigorous science. Systematic searches employed precise mapping, snow compaction analysis, and optical surveys to identify the dark shapes scattered across the ice. Once retrieved, meteorites were transported to laboratories where isotopic composition, mineralogy, and organic molecules were analyzed. Some fragments carried evidence of water-altered minerals, suggesting histories of interaction with liquid environments, while others contained traces of organic compounds, tantalizing hints at the chemistry of life beyond Earth. Antarctica became a cosmic time capsule, preserving the debris of planetary formation and offering scientists a rare, unbroken record of solar system history. Each rock told a story millions or even billions of years in the making, bridging the gap between the frozen Earth below and the infinite expanse above. Meanwhile, subglacial lakes continued to reveal astonishing biological and chemical complexity. Researchers discovered that microbial communities, trapped for millions of years beneath kilometers of ice, had evolved survival strategies unknown in more temperate habitats. Some relied on chemosynthesis, deriving energy from minerals and chemical reactions rather than sunlight, while others demonstrated extreme metabolic dormancy, capable of reanimation after prolonged stasis. These findings forced a re-evaluation of the conditions under which life might exist, providing analogues for the icy moons of the outer solar system and the shadowed subsurface of Mars. Antarctica, in these moments, was no longer just a place on Earth. It was a window into extraterrestrial possibility, a terrestrial rehearsal for understanding the distribution of life in the cosmos. The interplay between geology and astrobiology became increasingly evident. Ice cores not only revealed climatic history, but also contained traces of ancient cosmic impacts, dust, and even organic compounds delivered by meteorites. Researchers began to synthesize these observations into holistic models, connecting the survival of life in subglacial lakes with the history of cosmic material preserved in ice. Antarctica emerged as a singular environment where disciplines intersected: glaciology, biology, chemistry, planetary science, each layer of study informing the others, and each discovery deepening the sense that the continent was a microcosm of the universe itself. Technological innovation followed the demands of these investigations. Drills capable of penetrating kilometers of ice were designed to maintain sterile conditions, preventing contamination of ancient ecosystems. Remote sensors monitored environmental variables over vast distances, transmitting streams of data from the polar plateau to laboratories thousands of miles away. Even the construction of research stations required ingenuity. Energy efficiency, insulation, and life support systems had to operate in conditions that would quickly disable conventional infrastructure. In this sense, Antarctica became both a proving ground and a template, anticipating the engineering challenges that would arise on Mars or the Moon, and testing human capacity to observe, adapt, and endure. The philosophical undertones of these early investigations grew more pronounced with each expedition. Antarctica, once dismissed as a remote curiosity, had become a canvas upon which humanity could project questions about resilience, adaptation, and survival. The continent taught lessons not only in science, but in patience and humility. It demanded that researchers move slowly, observe carefully, and accept the constraints imposed by an environment far more powerful than themselves. The very act of studying life in isolation, ice, and darkness reflected a larger human yearning to understand our place in a universe that is vast, indifferent, yet occasionally remarkably hospitable to persistence. Through these cumulative efforts, the idea of Antarctica as a proxy universe solidified. The continent became a natural analogue for extraterrestrial worlds, a rehearsal space for planetary exploration, and a crucible for understanding life's adaptability under extremes. Every drilled core, every collected meteorite, every microbial sample contributed to an evolving portrait of a world where Earth and cosmos converged. In the harsh stillness, where snow and ice stretched unbroken to the horizon, science and imagination intertwined, revealing that the pursuit of knowledge often flourishes most profoundly in places that challenge not only intellect, but the very limits of endurance. Beneath kilometers of ancient ice, hidden from the light of the sun for millions of years, Lake Vostok whispered its secrets in silence. The lake, sealed beneath a frozen crust, was not a barren tomb of water and ice, but a reservoir of life persisting against every imaginable obstacle. Microbes, thriving in near-freezing darkness and nourished by minerals leached from surrounding rock, revealed a resilience that defied expectation. Extremophiles in this hidden world became living proof that life could endure in isolation, in conditions that seemed inhospitable to the warmth of organic existence. It was a revelation that reframed humanity's conception of survival. If life could flourish beneath the weight of kilometers of ice, Then perhaps it could endure beneath the frozen crusts of moons circling distant planets, in the permafrost of Mars, or in oceans hidden beneath ice shells light years away. In parallel, the discovery and study of the meteorite ALH 84001 from Antarctica ignited speculation about life beyond Earth. Scientists identified microscopic structures and mineral formations within the rock that hinted at the possibility of ancient Martian life, while debate over the interpretation continues. The implications were undeniable. Antarctica's frozen plains, by preserving such relics with unparalleled fidelity, had become a bridge to other worlds. Each meteorite carried with it fragments of planetary history, material that had traversed the solar system for eons, landing silently on Earth's southernmost continent. The ice, in its stark, patient stillness, became a cosmic archive, cataloguing not only Earth's extremes, but the remnants of planets beyond. The continent's skies offered another kind of revelation. The thin, dry air above Antarctica, coupled with months of uninterrupted darkness, allowed observatories to peer deeper into the universe than almost anywhere else on the planet. Telescopes, perched atop remote plateaus, captured faint infrared signals, cosmic microwave background radiation, and distant galaxies with a clarity unattainable elsewhere. In this way, Antarctica was not merely a proxy for other worlds. It became a window onto them, connecting the frozen Earth below with the expanse of space above. Scientists recognized that the environment, extreme yet stable, could serve as both analogue for human survival and as an unparalleled platform for observing the cosmos itself. The parallels between the Antarctic environment and Martian conditions became increasingly concrete. The continent's aridity, coupled with its extreme temperatures and nutrient-poor soils, mirrored the challenges anticipated on Mars. Experiments conducted on the ice simulated habitats designed for planetary exploration, testing closed ecosystems, robotic probes, and human adaptability. Each success, each observation, strengthened the link between Earth's extremes and the operational realities of living on another world. Antarctica was no longer simply analogous to space. It was actively preparing humanity for it, a rehearsal of survival, ingenuity, an observation at the planetary frontier. As extremophiles were catalogued, meteorites analyzed, and habitats tested, a pattern emerged. Each discovery reinforced the central thesis of Antarctica as both a mirror and a preparation ground. The continent's frozen expanse revealed the mechanics of life persisting against impossibility, the traces of worlds beyond, and the environmental parameters critical to sustaining existence beyond Earth. Researchers began to see a continuum, where microbial life beneath ice sheets, fragments of distant planets embedded in the snow, and the human struggle against isolation and cold were interconnected threads in a larger cosmic tapestry. Antarctica was simultaneously a teacher and a test, offering lessons in endurance, adaptability, and curiosity. The emotional resonance of these breakthroughs was palpable. Scientists, standing at the edge of subglacial lakes, observing microbes that had never seen sunlight, or holding meteorites that had traversed interplanetary space, often described a sense of humility and awe. They were witnesses to the persistence of life, the immensity of time, and the subtle, patient processes that connected Earth to the wider universe. Every experiment, every observation, deepened the understanding that survival, observation, and discovery were inseparable. Mastering the extremes of this frozen continent provided a guide for extending life, intelligence, and inquiry beyond its bounds. By the turn of the 21st century, Antarctica had evolved into more than a scientific curiosity. It had become a crucible for interplanetary understanding. Extremophiles revealed the possibilities of life in isolation. Meteorites connected Earth to the history of other planets. Observatories unveiled distant galaxies and cosmic signals. Habitats simulated life on Mars. And throughout it all, the ice itself persisted, indifferent, eternal, and profoundly instructive. Each discovery underscored a single truth. Antarctica was not merely a terrestrial analogue for space. It was an active preparation ground, a place where humanity rehearsed its first tentative steps into the cosmos, and where the boundary between Earth and the universe seemed to blur beneath layers of ice, cold, and quiet reflection. The significance of these discoveries deepened as the Antarctic ice revealed layers of history and complexity previously unimaginable. Drilling deeper into subglacial lakes like Vostok and Willen's uncovered chemical signatures that suggested not only survival, but slow, deliberate adaptation. Microbial ecosystems had persisted for millions of years in isolation, metabolizing energy from mineral-rich sediments, interacting in ways that resembled miniature, self-sustaining biospheres. Scientists began to see in these frozen reservoirs a parallel to potential life on distant icy moons, isolated, shielded from radiation, and evolving in extreme conditions. The endurance of these organisms offered a tangible blueprint for resilience in alien environments, a natural laboratory where evolutionary strategies could be studied in real time. Meteorite studies intensified this cosmic connection. Each recovered rock carried a history of violent journeys, tracing collisions and ejections across the solar system. Detailed isotopic analyses revealed conditions on Mars and asteroids at the moment of their formation. Some meteorites bore carbon compounds, the raw ingredients of life, preserved perfectly in the frigid Antarctic environment. Scientists speculated that if these compounds could survive the interplanetary journey and the freezing grip of the ice, then perhaps life's building blocks were not only resilient, but ubiquitous. Antarctica's ice was not just preserving history, it was demonstrating the extraordinary continuity between Earth and the broader cosmos. A frozen archive linking our world with distant, unseen environments. Astronomy from the Antarctic plateau further enriched this narrative. Telescopes stationed atop the high, dry plateaus could detect infrared signals obscured elsewhere by atmospheric moisture. These observatories captured faint glimmers from the earliest galaxies, observed subtle variations in cosmic microwave background radiation, and detected exoplanets orbiting distant stars. The clarity of the polar skies revealed patterns in light and energy that mirrored the clarity of the ice below. Both were ancient, pure, and revealing in ways that defied conventional measurement. In essence, Antarctica offered a dual perspective, the cosmos above and the extremes below, a simultaneous reflection of the vast and the intimate, the interstellar and the terrestrial. Simulated Mars habitats on the ice began to yield unexpected insights. Engineers and biologists collaborated to test energy efficiency, life support systems, and closed-loop ecological designs in extreme cold and isolation. Volunteers endured weeks of sensory monotony, limited mobility, and sub-zero temperatures, learning how to maintain physiological and psychological stability while conducting precise scientific measurements. These experiments transformed theory into lived experience. Antarctica became a stage for preparation. Astronauts could simulate months-long missions. Robotic systems could be tested in conditions of low moisture and extreme cold. And every failure or adaptation refined humanity's understanding of what survival truly required beyond Earth. The continent's unique dryness offered another revelation. The McMurdo dry valleys, almost entirely devoid of precipitation, mirrored the aridity of Martian terrain with uncanny accuracy. Salt-encrusted soils, exposed bedrock, and sparse microbial life created a natural analogue for the red planet. Field studies in these valleys provided critical data for designing rovers, drills, and life detection instruments. Each step taken across this desolate terrain echoed the cautious exploration that would one day occur on Mars. A rehearsal grounded not in imagination, but in the tactile reality of Earth's harshest extremes. In the midst of these scientific achievements, the emotional resonance of discovery persisted. Observers often described the awe of standing in these landscapes, knowing that they were witnessing phenomena both alien and intimately connected to their own existence. Meteorites whispered tales of other worlds. Microbes carried messages of survival across eons. Observatories captured the faint echoes of galaxies long vanished. Each breakthrough was not merely technical, it was existential, a reminder of life's persistence, the fragility of human endeavor, and the quiet, patient enormity of the universe. Antarctica, through these breakthroughs, became more than a mirror of space. It became an active participant in humanity's journey outward. It was a proving ground for life, a preservatory for cosmic relics, and a laboratory where the mechanics of survival and observation were tested under extremes. The discoveries here transformed not only scientific understanding, but human imagination, instilling a conviction that the study of Earth's edges could illuminate the possibilities of life, adaptation, and endurance throughout the cosmos. Even seemingly subtle observations carried profound implications. The behavior of ice sheets, the flow of glaciers, the chemical gradients in subglacial waters, all hinted at processes that might govern environments far beyond our planet. The ice became a model system, a complex, interactive matrix where lessons learned about resilience, energy flow, and adaptation could inform the design of habitats, instruments, and exploratory strategies for space missions. Antarctica, in this sense, was no longer merely analogous to other worlds. It was an experimental extension of them, a living laboratory where Earth itself rehearsed the mechanics of cosmic discovery. Through the quiet accumulation of these breakthroughs, a central realization emerged. Antarctica was preparing humanity for the universe. Extremophiles, meteorites, dry valleys, subglacial lakes, and observatories were not isolated phenomena. They were part of an interconnected system, revealing principles of life, survival, and cosmic connection. Each discovery deepened the link between the frozen continent and the vast, uncharted expanses of space, reinforcing a vision of Earth as both cradle and proxy for exploration, a place where the frontiers of science, endurance, and imagination converge in the endless whiteness beneath the frozen expanse. Life persisted in places that seemed impossible. Microbes were discovered in briny veins within ice, in subglacial lakes untouched for millions of years, in sediments sealed from the world above. These extremophiles thrived in darkness, in temperatures so low that chemical reactions barely stirred, in isolation so complete that human observers could scarcely imagine it. Their existence challenged assumptions about the limits of life. Here, at the cold and quiet edge of the planet, biology had been forced to adapt in ways that blurred the line between survival and endurance, between the possible and the improbable. The very presence of these organisms raised a question that reverberated across scientific disciplines. If life could endure here, in the hidden, unlit recesses of Earth, why not on Mars, beneath Europa's icy shell, or in the oceans of Antarctica's role as a cosmic archive deepened with each discovery. Meteorites preserved in the ice, some originating from Mars itself, carried within them the history of distant worlds. Some bore the traces of organic molecules, subtle structures suggesting the possibility that life, or at least its building blocks, might have traveled between planets. The notion of panspermia, once speculative, gained a visceral credibility in the pale, unbroken expanse of the polar plains. Here, fragments of Mars, of asteroids, of ancient cosmic debris rested silently in the ice, waiting for human hands to uncover them. The frozen continent became a laboratory not only for life on Earth, but for the profound question of life's distribution across the cosmos. Ice cores, drilled through layers of millennia, revealed Earth's own hidden history, trapped atmospheres, fluctuations in greenhouse gases, traces of volcanic eruptions, cosmic impacts. Each cylinder of ice was a vertical map of time, a testament to the planet's long memory. Scientists realized that studying these records offered parallels to the observation of exoplanet atmospheres. Just as gases trapped in Antarctic ice could reveal the history of Earth's climate, spectral readings of distant worlds could reveal their composition, their potential for life, and even the echoes of catastrophic events. The frozen layers became a bridge between planetary science and astronomy, a reminder that the past of Earth and the study of other worlds were entwined. Like reflections across a cosmic mirror, human endurance under these extremes added another layer of mystery. Isolation studies conducted in Antarctic stations revealed subtle yet profound changes in cognition, mood, and perception. Months of uninterrupted darkness, sensory monotony, and extreme cold reshaped not only behavior but consciousness itself. Minds began to bend under the weight of seclusion. Time felt elongated, perceptions sharpened and distorted, emotional thresholds altered. These observations offered a cautionary tale for humanity's cosmic ambitions. The human mind, delicate yet resilient, would be tested as severely as the body, perhaps more so, when it ventured beyond Earth's familiar constraints. The ice, in its silent and indifferent observation, became a teacher of limits, a rehearsal space for the psychological rigors of interplanetary exploration. The unsettling truth of Antarctica lay in its duality. It was at once a reflection of Earth's fragility and a rehearsal for humanity's cosmic future. The countenance extremity revealed vulnerability, how life could endure only under precise conditions, how human survival depended on ingenuity, preparation, and respect for environment. Yet it also hinted at potential resilience embedded in life itself, the possibility of existence where none was thought feasible, and the subtle yet powerful lessons that extreme Earth environments could teach about the universe beyond. The frozen continent became a stage where the persistence of life, the traces of cosmic history, and the endurance of human consciousness converged, creating a profound reflection on our place in the cosmos. With each drilled core, each recovered meteorite, each observation of microbial endurance, Antarctica deepened its mystery. The continent was no longer merely extreme. It was exemplary. It held lessons for planetary science, astrobiology, climate understanding, and human psychology simultaneously. It invited speculation tempered by rigor, wonder grounded in data, and reflection drawn from experience. In its ice, Antarctica carried the memory of the Earth and the echoes of worlds beyond, challenging observers to reconsider the boundaries of possibility. And in the stillness, under pale skies that stretched endlessly toward the stars, one could sense the convergence of time, space, and life. Antarctica, silent and immutable, posed a subtle yet insistent question. If life could endure here, in the margins of our world, what did it reveal about life elsewhere? If humanity could survive, adapt, and reflect in this frozen expanse, what might that teach us about stepping beyond Earth into a cosmos both vast and unknowable? The mystery deepened with every expedition, every measurement, every observation, as the ice itself seemed to whisper of resilience, connection, and the fragile, persistent dance of life across planets, time, and space. Beyond the microbial communities and ice-strapped meteorites. Antarctica began to reveal enigmas that transcended biology and geology. Subglacial lakes, some larger than entire cities, harbored chemical and thermal gradients that were complex, almost alien in their subtlety. These lakes were not static reservoirs. They were dynamic systems, circulating slowly beneath kilometers of ice, chemically active and isolated from the surface for millions of years. Scientists discovered that microorganisms were not merely surviving passively. They were metabolically active, cycling nutrients in ways that suggested long-term equilibrium within sealed ecosystems. The profound implication was that life could not only endure in isolation, but could thrive in a delicate balance, entirely removed from sunlight, atmospheric exchange, or seasonal cycles. Antarctica had become a laboratory for observing life in conditions that mirrored those suspected, beneath Europa's icy crust or Enceladus's hidden ocean. A rehearsal for understanding alien biospheres without ever leaving Earth. Even the ice itself carried secrets, encoded in patterns of stratification and trapped particulates. Layers of volcanic ash revealed eruptions that had once encircled the globe, while microscopic dust captured evidence of solar and cosmic activity over hundreds of thousands of years. Researchers began to interpret these as a cosmic ledger, a record of events that linked Earth to the wider solar system. Each ice core was a temporal map, recording collisions with meteoritic bodies, shifts in the planet's orbit, and subtle fluctuations in solar intensity. Antarctica's ice was a mirror not only of Earth's climate history, but of the broader celestial mechanics that govern planetary environments. It demonstrated that to understand life on other worlds, one must first understand the intricate interplay of planetary forces here. Beneath our own frozen skies, meteorites continued to enrich this cosmic narrative. Some contained complex organic molecules, including amino acids, reinforcing the tantalizing possibility that the seeds of life may be scattered across planets. Others preserved isotopic ratios that allowed reconstruction of planetary processes long vanished. The ice acted as both archivist and magnifier. Fragments that might have eroded or degraded elsewhere were preserved in pristine condition, offering a direct window into the formation, evolution, and chemical diversity of the solar system. In this frozen archive, the story of the cosmos was tangible, held in the same environment that tested the limits of human endurance, microbial resilience, and technological innovation. Human isolation studies, meanwhile, revealed psychological dynamics as subtle and intricate as the chemical gradients in subglacial lakes. Extended confinement in Antarctic stations showed how sensory monotony, circadian disruption, and environmental extremity reshaped perception. Subjects experienced temporal distortion, altered emotional processing, and heightened sensitivity to social dynamics. These changes were not merely academic. They were practical indicators of how humans might respond during months-long missions to Mars, the Moon, or even interplanetary habitats. The ice demanded patience, reflection, and self-awareness. Here, in the margins of human experience, the mind was tested as rigorously as the body. Antarctica had become a theater for understanding cognition, endurance, and the subtleties of adaptation in conditions far removed from the familiar warmth of Earth's temperate zones. The continent's dual role as a record keeper of cosmic and terrestrial history, and as a laboratory for life in extreme isolation, led to profound philosophical reflection. Antarctica revealed that the boundaries of existence were not fixed but fluid, that life could endure where it seemed impossible, and that Earth itself could serve as both a model and a rehearsal space for the exploration of worlds beyond. Each expedition, each drill, each observation deepened the realization that humanity's understanding of life and survival was inseparable from the study of extremes. The frozen continent held lessons not only about biology and chemistry, but about perspective, about our fragility, our resilience, and our potential to extend life beyond the confines of our planet. Technological innovation followed the demands of these extremes. Autonomous probes were developed to explore subglacial lakes without contaminating them. Remote sensors monitored chemical fluxes and microbial activity across vast, inaccessible regions. Imaging systems were refined to detect subtle biological signals under kilometers of ice. Every advance not only expanded scientific understanding of Antarctica, but provided critical insight into the tools and methods required for extraterrestrial exploration. In this sense, the continent served as both classroom and proving ground, a place where human ingenuity and natural extremity converged, revealing lessons as practical as they were profound. And yet, for all these discoveries, Antarctica retained its mystery. The extremophiles, the ice-bound meteorites, the subglacial lakes, and the silent expanse of the dry valleys reminded observers that understanding is always provisional. For every answer uncovered, new questions emerged. How deep could life endure beneath the ice? Could complex organisms exist undetected in subglacial ecosystems? How might these analogues inform the search for life on Europa, Enceladus, or distant exoplanets? The frozen continent remained a threshold, a place where certainty dissolved into awe, and where each discovery opened portals to questions that stretched far beyond Earth. In this stillness, Antarctica became both mirror and rehearsal, reflecting the fragility of our planet and the endurance of life, while preparing humanity for the challenges of the universe. The mystery deepened with every observation, every core, and every discovery, revealing a frozen landscape that was simultaneously terrestrial and cosmic. It whispered a singular, profound lesson: to understand life, survival, and the universe itself, one must confront extremes, embrace uncertainty, and observe with patience, humility, and reverence beneath the serene, white expanse of Antarctica, hidden deep within the ice. Humanity has built instruments capable of glimpsing the universe in ways previously unimaginable. The IceCube Neutrino Observatory, a lattice of detectors suspended in a cubic kilometer of pristine ice, listens for the faintest whispers of particles that traverse the cosmos without resistance or hesitation. Neutrinos, nearly massless and invisible, pass through planets, stars, and galaxies as if they were not there at all, leaving only subtle traces for those prepared to observe. Here, in this frozen desert, Earth itself becomes a lens, the ice a perfect medium for revealing the otherwise imperceptible rhythms of the universe. The IceCube experiment is a testament to human ingenuity, engineering, and patience. Thousands of detectors, lowered into melted shafts that refreeze around them, wait silently, capturing flashes of Cherenkov light that signal the passage of a single neutrino. Each detection is a triumph, a confirmation that even in a landscape of extreme cold and isolation, humans can devise instruments that extend perception far beyond our senses. The ice itself, solid and ancient, becomes a cosmic observatory, a medium that transforms the continent from a remote wilderness into a window onto distant galaxies, exploding stars, and the fundamental particles that underpin reality itself. Above the ice, the air carries another frontier of exploration. Balloon-borne telescopes, launched from stations like McMurdo and the Amundsen-Scott South Pole Station, drift silently into the stratosphere, measuring the cosmic microwave background radiation with exquisite precision. These balloons rise above Earth's atmosphere, where water vapor would otherwise blur the faint echoes of the universe's infancy. From this vantage, scientists peer back nearly 14 billion years, tracing the contours of time and energy imprinted on the cosmos at its birth. Antarctica, in these experiments, becomes both laboratory and telescope, offering the clarity and stability necessary to pursue the faintest cosmic signals. The extremity of this environment tests more than instruments. It tests human endurance and ingenuity. Researchers live for months in isolation, tending equipment, calibrating sensors, and enduring sub-zero temperatures that sap strength and slow time. Supply chains must traverse hundreds of kilometers of ice, helicopters must navigate blizzards, and even the simplest mechanical failure becomes a formidable challenge. Here, survival and discovery are intertwined, a constant negotiation between human limitations and the relentless demands of extreme science. Antarctica has become a proving ground, not only for machines and instruments, but for ideas about what is possible in conditions that mimic the isolation and hostility of space itself. Collaboration flourishes in this frozen expanse. Scientists from dozens of nations converge, united by a singular purpose: to understand the universe. Language, nationality, and politics recede against the shared awe of discovery. In the extreme quiet of the polar plateau, humanity rehearses the international cooperation that will be essential for interplanetary exploration, for building colonies, telescopes, and laboratories beyond Earth. Antarctica's isolation, its harshness, and its unforgiving nature foster a rare clarity. Survival depends on ingenuity, preparation, and the collective knowledge of many minds. Through these converging efforts, Antarctica becomes a crucible for the edge of human possibility. The neutrinos detected deep in the ice, the cosmic background observed from high above, and the extreme conditions endured by researchers collectively redefine the boundaries of science. They reveal that understanding the universe demands more than intellect. It requires patience, resilience, and the courage to work at the limits of both technology and human endurance. The continent is no longer merely a proxy for other worlds. It is an environment that stretches the mind and body, shaping those who seek to explore beyond our planet. Here, at the extreme edge of Earth, instruments measure and humans confront both the immensity of the cosmos and their own limitations. Antarctica, in its stillness and severity, becomes a mirror and a mentor, reflecting the fragility of life, the audacity of curiosity, and the boundless scale of the universe. Every detection, every observation, every experiment is a reminder that science is a dialogue not only with nature but with possibility itself. In this frozen frontier, humanity rehearses its first steps into the cosmos, testing tools, endurance, and imagination against a landscape as demanding and enigmatic as the universe itself. The extremity of Antarctic science extends far beyond instruments and isolated laboratories. The continent's natural architecture, its thick, transparent ice, its stable yet frigid air, its vast emptiness allows phenomena to be observed in ways impossible elsewhere. Cosmic rays, for example, strike the polar plateau with greater intensity, their paths less scattered by atmospheric moisture or geomagnetic interference. Detectors embedded within the ice capture these energetic visitors, tracing their origins to supernova, distant quasars, or the collisions of galaxies billions of light-years away. In this sense, Antarctica is not merely passive. It actively shapes the pursuit of knowledge, amplifying signals that might otherwise be lost, allowing humanity to witness events across unimaginable distances. Yet the ice is also a challenge, an adversary as much as a medium. Extreme cold slows the movement of materials, causes mechanical failures, and demands engineering solutions that are elegant in their simplicity, yet unyielding in precision. Drilling rigs must operate in temperatures below 50 degrees Celsius, Electronics must survive without overheating or freezing, and even the lightest miscalculation can compromise a delicate experiment. Each technological breakthrough, each functional instrument, is a testament to human ingenuity, a tangible triumph over one of the most inhospitable environments on Earth. Antarctica transforms abstract theoretical designs into practical realities, where ideas are tested against the relentless scrutiny of nature itself. The extreme edge of science is also philosophical. In working here, researchers confront the juxtaposition of human fragility and cosmic immensity. Standing atop a plateau of glacial ice, with the vast whiteness stretching to the horizon under a sky of impossible clarity, one cannot help but feel the weight of scale. Particles smaller than atoms, traveling across the universe for eons, are detected in the ice below one's feet. Cosmic microwave radiation, the echo of the Big Bang, is traced in subtle temperature fluctuations by instruments hovering above in balloon-borne observatories. Antarctica provides a rare vantage where the infinitesimal and the infinite converge, forcing reflection on humanity's place in the cosmos and the fragility of life. Amidst its overwhelming IMMMSITY, collaboration in this extreme environment has reshaped scientific culture. Antarctic research demands international coordination, sharing data, resources, and expertise. Scientists from diverse nations work side by side, united by shared objectives that transcend borders and politics. Each mission becomes a microcosm of the cooperation required for humanity to explore beyond Earth. The continent, in its harsh neutrality, levels hierarchy and fosters collaboration, teaching lessons in diplomacy, patience, and the collective pursuit of understanding. It foreshadows the challenges of multinational efforts to build orbital stations, lunar habitats, or Martian colonies, where survival, innovation, and diplomacy will be inseparable. Moreover, Antarctica stretches the limits of imagination. The extremity of its environment inspires scientists and engineers to envision possibilities previously thought impossible. Life at sub-zero temperatures and near total isolation challenges assumptions about biological resilience. The clarity of the polar skies invites contemplation of the universe's earliest moments. Neutrinos, cosmic rays, and meteorites become tangible threads linking Earth to distant phenomena. Each discovery invites speculation. How might similar extremes exist elsewhere in the solar system or galaxy? What adaptations might life evolve in those conditions? Antarctica becomes a canvas for the mind, a place where empirical observation and imaginative reasoning coexist, reinforcing the connection between earthly extremes and extraterrestrial frontiers. Even the human body is a laboratory here. Researchers study the physiological effects of prolonged exposure to cold, hypoxia, and isolation, providing critical insight into what will be required for long-duration space missions. Energy expenditure, circadian rhythm disruption, and psychological resilience are measured and interpreted, turning the human organism into a living instrument of discovery. Survival in Antarctica is an active experiment in adaptation, testing the thresholds of endurance and the strategies necessary for existence in environments both extreme and unfamiliar. In this sense, the continent is a mirror. It reflects the limits of human capability while simultaneously offering a rehearsal for the challenges of exploration beyond Earth. Antarctica's extremity is also temporal. Instruments record signals that have traveled across billions of years, while ice preserves the echoes of Earth's own past, from atmospheric composition to ancient cosmic impacts. This duality of time observing the distant universe while simultaneously interrogating the frozen memory of Earth provides a perspective that is both humbling and awe-inspiring. Scientists come to understand that exploration is not a linear process. It is a conversation across scales of time and space, a dialogue between the infinitesimal and the eternal. In every measurement, every deployment, every observation, Antarctica demonstrates that the edge of science is defined not only by what is known, but by the environment in which discovery is pursued. The continent tests instruments, human resilience, and the limits of imagination simultaneously. It is a proving ground for physics, engineering, biology, and psychology alike, a place where the physical world demands rigor and precision, where the mind must confront extremes of scale, and where the silence of ice amplifies the whispers of the cosmos. In this convergence, Antarctica becomes more than a continent. It becomes a threshold, the extreme edge where Earth prepares humanity for the universe, and where the boundaries of possibility are both measured and transcended. Antarctica's frozen expanse has long been recognized not merely as a continent at the edge of the Earth, but as a mirror for worlds beyond our own. Scientists have repeatedly returned to its glaciers, valleys, and subglacial lakes, discovering that this icebound wilderness offers the closest terrestrial analogue for the Martian surface. The McMurdo dry valleys, stark and desolate, echo the arid, rocky plains of Mars, salt deposits, frozen soils, and sparse microbial life mirror the conditions of the red planet, where water exists only in trace brines and survival is a testament to adaptability. Here, on Earth's coldest plateau, the first experiments in extraterrestrial survival are conducted not in but in the very material and conditions that resemble those of alien worlds. Within the ice itself, microorganisms endure in a state of remarkable dormancy. Trapped beneath kilometers of frozen water, they have survived for millions of years, metabolically paused yet fully viable when revived. Studies suggest that these organisms withstand desiccation, radiation, and extreme cold far beyond the tolerance of most known life. The implications are profound. If microbes can persist here for geological time, similar survival may be possible on Mars under Europa's ice, or within the briny oceans of Antarctica. In this mainstream perspective, is more than a cold desert, is a living archive of resilience. A laboratory where scientists can observe the strategies that life might employ to endure in the universe. Meteorites found scattered across the ice further illuminate Earth's cosmic connectivity. Rocks originating from Mars, some containing complex organic molecules, lie preserved like time capsules within the glaciers. Isotopic analysis reveals violent histories, collisions on distant worlds that ejected material into space, traversing millions of kilometers before landing here. The ice acts as both preserver and recorder, allowing scientists to reconstruct the trajectories and compositions of these extraterrestrial visitors. Such discoveries reinforce a mainstream theory that material, and perhaps even life's building blocks, may traverse the solar system, linking planets in ways that were once purely speculative. Antarctica, in this sense, is not simply an analogue. It is a witness to cosmic exchange. Ice cores offer yet another window into planetary processes. Layers accumulated over hundreds of thousands of years capture fluctuations in temperature, atmospheric gases, and chemical composition. By modeling the greenhouse gases, isotopic ratios, and trapped particulates, scientists can simulate how planetary atmospheres evolve under varying conditions. The lessons extend beyond Earth. By understanding the climate history preserved in Antarctic ice, researchers can better predict the atmospheric dynamics of exoplanets and infer the potential for habitability elsewhere. The ice becomes a proxy for distant worlds, a laboratory where terrestrial records illuminate universal patterns. Meanwhile, the polar plateau has proven invaluable for fundamental physics. Neutrino detection, conducted deep within the ice, allows researchers to observe cosmic phenomena that are otherwise invisible. These near-massless particles travel through planets, stars, and galaxies, yet interactions with Antarctic ice produce tiny flashes of light detectable by sensitive instruments. Each neutrino captured is a direct probe of cosmic events, supernova, gamma-ray bursts, or interactions at the edge of known physics. Antarctica, in the mainstream view, is thus indispensable not only for astrobiology and planetary analogues, but for expanding humanity's understanding of the universe itself. From a practical perspective, Antarctica is a rehearsal space for human exploration. Habitats established on the plateau test not only technology but human endurance, offering lessons in isolation, resource management, and psychological adaptation. Researchers experience long periods of darkness, extreme cold, and limited mobility, conditions that mimic those of long-duration missions to Mars or deep space stations. The mainstream scientific consensus holds that the skills, technologies, and observations gained here are directly translatable to humanity's future among the stars. In every dimension, biology, geology, climatology, and astrophysics, Antarctica is framed as an indispensable platform. The continent's extremity is not a barrier but a tool, a natural laboratory in which hypotheses about life, planetary processes, and cosmic phenomena are tested in the harshest conditions available on Earth. Mainstream theories converge on a singular truth: preparation for space begins on the ice. From microbial survival to cosmic observation, from human endurance to planetary modeling, Antarctica offers both the conditions and the lessons necessary to expand the reach of science beyond the confines of this planet. Through these converging perspectives, the continent emerges as more than a frozen wilderness. It is a nexus where Earth and cosmos meet, a crucible for ideas, instruments, and endurance. In the mainstream narrative, Antarctica is a cornerstone of humanity's journey outward, a place where the universe can be glimpsed through ice, where the past of distant worlds is preserved in frozen rock, and where life's resilience on Earth offers the first promise of life beyond it. Here, on this edge of the world, science rehearses the limits of possibility, preparing both mind and machine for the challenges that await beyond the atmosphere. In the vast, uncharted expanse of space, Antarctica's role as an Earth analogue extends into subtle chemical and physical dimensions that are often overlooked. Beyond surface dryness and temperature, the continent offers extreme radiation environments, both cosmic and solar, that mimic conditions on Mars and in near-space habitats. The thin atmosphere over the polar plateau allows ultraviolet and cosmic radiation to penetrate more intensely, creating conditions under which DNA and cellular structures are stressed in ways analogous to extraterrestrial exposure. Studies of microbial survival under these conditions have shown remarkable resilience, demonstrating that even the most delicate forms of life can endure prolonged exposure when shielded by ice or rock. Such findings provide invaluable data for designing radiation-protected habitats on other planets and for understanding how life might persist in the harshest corners of the solar system. The geophysical characteristics of Antarctica further enhance its value as a planetary analogue. Subglacial lakes, isolated beneath kilometers of ice, present environments entirely removed from surface influence. Their chemistry is shaped by slow geothermal heating, mineral interactions, and microbial activity, creating stable ecosystems that exist in perpetual darkness. These lakes allow researchers to study biogeochemical cycles in isolation, yielding insights into how life could function under the icy crusts of moons such as Europa or Ganymede. The detection of microbial mats, metabolically active but reinforces the theory that life can survive in equilibrium with extreme conditions for millions of years, enduring in ways that challenge conventional assumptions about meteorites scattered across the Antarctic ice sheet continue to illuminate planetary connections. Each rock is a fragment of cosmic history, carrying isotopic signatures and organic compounds that reveal processes occurring millions or even billions of years ago on other worlds. By studying the distribution and composition of these meteorites, scientists have reconstructed the dynamics of planetary collisions and the potential pathways of material exchange between Mars and Earth. The mainstream interpretation is compelling. Antarctica acts as a natural archive, preserving these interplanetary visitors in a pristine state, offering an unbroken record of solar system history. Through this frozen lens, researchers can explore fundamental questions about the transfer of life's building blocks across planets, a process that may have contributed to the origins of life on Earth itself. Climate modeling derived from ice cores provides another critical tool. By analyzing trapped gases, particulates, and isotopes, scientists have reconstructed Earth's climate over hundreds of thousands of years. These records reveal correlations between atmospheric composition, solar cycles, and global temperatures, offering a template for understanding planetary atmospheres elsewhere. For example, variations in carbon dioxide and methane concentrations over glacial cycles serve as analogues for potential atmospheric processes on Mars, Venus, or distant exoplanets. In mainstream theory, these observations are crucial. They enable the development of predictive models for climate stability and habitability beyond Earth, connecting terrestrial paleoclimatology to the search for life across the cosmos. Antarctica also provides a unique platform for testing instrumentation designed for space missions. Autonomous rovers, remote sensors, and robotic sampling devices are deployed across glaciers and subglacial lakes, where they must function under extreme cold, low humidity, and high radiation. These trials yield critical insights into durability, energy efficiency, and operational reliability, directly informing the design of Martian landers, Europa probes, and lunar research stations. The continent serves as both a proving ground and a calibration site, allowing scientists to anticipate challenges, refine methodologies, and validate the precision of instruments intended for environments far beyond Earth's surface. Human research teams, meanwhile, offer another layer of insight: the physiological and psychological responses to prolonged Antarctic deployment stress, isolation, circadian disruption, and extreme cold exposure mirror those expected on long-duration space missions. Mainstream theory recognizes that understanding human adaptation in Antarctica is as vital as studying microbes or meteorites. The continent functions as a living laboratory for human endurance, providing data on nutrition, mental health, and teamwork under conditions that approximate interplanetary travel. Each expedition becomes a rehearsal for the human experience of living in closed systems far from home, emphasizing that the limits of survival are as much psychological as they are physical. Even Antarctica's optical and radio-quiet conditions contribute to mainstream scientific thought. High-altitude plateaus and stable, dry air allow telescopes to detect faint cosmic signals with minimal atmospheric interference. These observations complement neutrino and particle physics research, providing a holistic view of the universe from the smallest particles to the largest structures. Mainstream interpretation positions Antarctica as an indispensable observatory, one that bridges disciplines and scales, connecting the terrestrial extremes of Earth to the cosmic extremes of the universe. Ultimately, The mainstream perspective frames Antarctica as an irreplaceable nexus for preparation, observation, and discovery. From microbial survival to planetary modeling, from meteorite archives to neutrino detection, the continent integrates multiple lines of evidence into a coherent narrative. That extreme environments on Earth offer both lessons and tools for understanding the cosmos. It is a place where scientific theory is tested against the harshest conditions available on the planet, where instruments are refined, life is studied in its most austere forms, and human endurance is measured against unforgiving isolation. Antarctica is, in every sense, a laboratory at the edge of possibility, offering a bridge between the known world and the universe beyond. In the deepest folds of Antarctic ice lie fragments of stories that may extend far beyond our planet. Meteorites embedded in these frozen layers carry more than geological history. They carry the tantalizing possibility that life itself is a traveler. The panspermia hypothesis suggests that life, or at least its building blocks, may have arrived on Earth via interplanetary debris, seeding our world in a cosmic exchange preserved within the continent's ice. Each meteorite becomes a messenger from a distant past, a fragment of other worlds silently whispering across the millennia. While mainstream science treats this idea with cautious optimism, the frozen deserts of Antarctica make it plausible, providing the preservation necessary to sustain organic molecules, or even dormant microorganisms through vast stretches of time. The ice is a temporal capsule, a record of cosmic journeys, and a stage on which the question of life's universality plays out. Subglacial lakes add another layer of speculation, their hidden waters sealed beneath kilometers of ice for millions of years. These alien seas are chemically and thermally isolated from the surface, circulating slowly in darkness, untouched by sunlight or human interference. Scientists speculate that the life forms within could mirror the ecosystems that may exist beneath the icy crust of Jupiter's moon, Europa, or Saturn's microbial mats, extremophiles. An unknown biochemical pathways hint at the possibility of life that diverges from terrestrial norms, adapted to conditions that seem impossibly hostile. Antarctica becomes a proxy for distant worlds, a rehearsal for discovering life forms that may share only a distant kinship with the DNA-based life we know. The ice conceals not just water, but the imagination of what life can endure, what it can become, and how it might manifest on other planets. Beyond biology, Antarctica tests the human psyche in ways that border on the philosophical. Long-term isolation, monotony, and sensory deprivation at research stations provoke introspection, hallucinations, and shifts in temporal perception. Some speculative theorists propose that these conditions are not only analogues for survival in space, but also models for understanding consciousness during interstellar travel. If humanity were to voyage to the stars for years or decades, what would the mind endure in the cold, unyielding vastness of void? Antarctic expeditions offer a living laboratory for this extreme psychological frontier, suggesting that survival in space is as much a question of mental resilience as physical endurance. The frozen desert becomes a mirror, reflecting not only the universe outside but the universe within. Speculation extends even to microbial evolution. Could Antarctica harbor life with biochemistries alien to Earth's familiar patterns? Some fringe researchers propose that the extreme cold, radiation, and isolation might encourage metabolic pathways fundamentally different from those found in temperate environments. Enzymes that function in near absolute zero, membranes resistant to intense radiation, and energy cycles that exploit quantum effects could all be realized in microorganisms surviving beneath the ice. These ideas remain unproven, yet they are grounded in observation. Life in Antarctica does defy expectations. prompting the question of whether extremes can foster entirely novel biochemistry. The continent, in this light, is both laboratory and incubator for life that challenges our definitions of the possible. Quantum biology offers another avenue of contemplation. Some researchers speculate that survival in extreme cold may involve quantum mechanisms, coherence in energy transfer, entanglement in molecular interactions that allow life to maintain metabolic functions in conditions approaching chemical stasis. If true, these mechanisms could illuminate strategies for life elsewhere in the cosmos, where energy is scarce and environments are unforgiving. Antarctica's frozen depths may contain clues not only to survival, but to the fundamental nature of life itself, revealing that biology can operate at the intersection of physics and chemistry in ways we are only beginning to imagine. Poetically, Antarctica becomes a cradle and a mirror. It is a place where the fragility of life is exposed to the harshest elements, yet where resilience, ingenuity, and adaptation are illuminated. The frozen continent preserves evidence of the cosmos, shelters life in exoplanets, and reflects humanity's quest to reach beyond its terrestrial home. In the stillness of ice, the whispers of distant worlds converge with the echo of Earth's own history, inviting speculation that life is not confined to a single planet, a single biochemistry, or a single form of consciousness. Here, the speculative and the empirical coexist, entwined in a dance of possibility, guiding both the mind and the imagination toward the cosmos. Through these lenses, panspermia, subglacial analogues, psychological resilience, novel biochemistry, and quantum survival, Antarctica emerges as more than a continent. It is a nexus of speculation and discovery, a threshold between what we know and what we dare to imagine. The ice, the hidden lakes, the preserved meteorites, and the enduring microbes form a narrative in which Earth and cosmos are inseparably linked, suggesting that the story of life is both ancient and universal, written not only on our planet, but across the stars themselves. In this speculative frontier, every grain of ice becomes a page, and every meteorite a chapter, in a story that stretches far beyond the boundaries of human knowledge. Antarctica's speculative allure extends to the idea that it may conceal ecosystems unlike any found elsewhere on Earth. Beneath its frozen crust, isolated pockets of water, nutrients, and geothermal heat create conditions so removed from the surface that life within could operate under principles entirely different from familiar biology. Some theorists envision organisms that utilize alternative solvents to water, or metabolic pathways that exploit rare chemical gradients frozen into the ice over eons. In this view, Antarctica is not merely a frozen desert, but a hidden laboratory, a testing ground for life's adaptability under extreme isolation, potentially offering glimpses into the diversity of life that could exist on distant worlds. These hypothetical forms of life challenge our understanding of survival, evolution, and the boundaries of the biosphere itself. The possibility of ancient microbial lineages preserved for millions of years opens further speculation. Some researchers suggest that these microbes might carry genetic or chemical signatures of life that arrive from other planets, perhaps delivered via meteorites during the early epochs of the solar system. If Antarctic ice harbors such relics, it could provide a direct connection to extraterrestrial life, at least to the chemical precursors that seeded it elsewhere. These frozen organisms become messengers from a cosmic past, their survival defying conventional limits and offering tantalizing hints that life is not confined to a single planetary cradle. The ice, in this sense, becomes a bridge between worlds, a medium through which we might read the story of life beyond Earth. Speculation also touches on the notion of Antarctica, as a model for extreme human adaptation in space. Long-term habitation in polar stations exposes researchers to prolonged darkness, extreme cold, and social isolation, conditions that mirror the psychological and physiological challenges of interstellar voyages. Scientists and psychologists alike have observed shifts in perception, mood, and cognition among those wintering on the plateau, prompting questions about consciousness under stress and isolation. Could humans on long-duration missions to Mars or beyond develop cognitive strategies or adaptations akin to those learned in Antarctica? Some fringe theorists suggest that the polar experience may offer insights not only into endurance, but into how the human mind interacts with vast, empty environments, both external and internal. The continent becomes a crucible for understanding consciousness in Mesa, a rehearsal for journeys into the silent reaches of space. Quantum survival mechanisms present another provocative avenue. Life at sub-zero temperatures and high radiation may exploit phenomena that appear almost otherworldly, quantum tunneling enabling chemical reactions that would otherwise stall. Coherence in energy transfer allowing cells to function near the limits of thermal stability, or entanglement phenomena that maintain metabolic processes over extended periods. Though these ideas remain largely theoretical, Antarctica offers the empirical stage where such possibilities might be observed indirectly. Microbial persistence under conditions that verge on stasis invites the speculation that life might operate at a level that intertwines biology and quantum physics, revealing strategies that could be mirrored in life forms elsewhere in the universe. Even the geochemical environment hints at cosmic interconnectedness. Minerals and gases trapped in subglacial lakes or embedded in ice cores may preserve isotopic ratios not only of Earth's past, but of interactions with solar and interstellar particles. Some fringe researchers speculate that these trapped particles could carry information chemical imprints of distant supernova, or even cosmic radiation signatures that influenced prebiotic chemistry. In this sense, Antarctica becomes a reading room for cosmic history, a place where the ice itself archives the dialogue between Earth and the universe, and where life's persistence may reflect the interplay of biology, chemistry, and astrophysics. Poetically, Antarctica represents the tension between fragility and endurance, between the known and the speculative. Its frozen landscapes are simultaneously hostile and revealing, a mirror of both our limitations and our potential. The possibility that unknown life exists beneath the ice, or that microbes preserved in ancient layers carry extraterrestrial origins, challenges the imagination and forces reflection on the universality of life. Antarctica, in these speculative theories, is not only a laboratory but a teacher, inviting questions about the resilience of life, the interconnectedness of worlds, and the ways in which existence persists in the face of extreme isolation. Finally, the continent evokes a philosophical resonance. The same ice that preserves meteorites from Mars may also cradle life in its most extreme form, suggesting that life is not bound to a single environment or chemistry. Antarctica becomes a crucible where the empirical and the imaginative intersect, where every discovery opens avenues for questions that extend beyond the physical world. It is a place where the poetic and the scientific converge, where the frozen silence encourages reflection on life's universality, where the extreme environment compels both rigor and wonder, and where the boundaries of possibility are tested as rigorously as the instruments and humans that endure within it. In this speculative realm, Antarctica becomes a cosmic mirror, reflecting both what life has achieved on Earth and what it might achieve elsewhere. It is a threshold between the observable and the imaginable, a place where microbes, ice, meteorites, and human explorers converge to illuminate the potential breadths of existence. Here, at the edge of knowledge, every fragment of ice, every isolated lake, and every preserved meteorite challenges our assumptions, suggesting that life, in its resilience and diversity, may be a universal phenomenon waiting to be glimpsed. In the quiet, frozen heart of Earth's most extreme continent, across the frozen expanse of Antarctica, modern science presses forward, moving deeper into ice, water, and sky in search of knowledge that bridges Earth and the cosmos. Drill rigs hum quietly over the stillness of glaciers, their long arms boring through kilometers of ice to reach the subglacial lakes that have lain sealed for millions of years. Within these isolated waters, untouched by sunlight or human influence, life may persist in forms entirely unfamiliar. Researchers descend into the silence of these hidden oceans, collecting samples with meticulous care, aware that each droplet could reveal new principles of biology, chemistry, and resilience. In these endeavors, Antarctica is no longer merely a metaphor for space. It is a literal laboratory for testing humanity's understanding of life under extreme conditions. Across the plateau, teams traverse the ice on long expeditions, sweeping its vast surface for meteorites that have traveled millions of kilometers from distant worlds. Each fragment recovered is a story etched in stone, a remnant of cosmic violence preserved perfectly in the ice. These meteorites carry isotopic signatures, organic compounds, and sometimes even microscopic structures that hint at processes on Mars, the Moon, and beyond. Continuous collection campaigns have transformed Antarctica into the largest natural cosmic archive on Earth, where every sample deepens our understanding of planetary formation, interstellar exchange, and the fragile threads connecting worlds. The ice preserves what time might otherwise erase, allowing scientists to study the history of the solar system as if it were written in frozen ink. Beneath the surface, the ice-cube neutrino observatory stretches across a cubic kilometer of Antarctic ice, its detectors listening for particles that traverse the universe unnoticed. Neutrinos, almost ghostly in their passage, rarely interact with matter, yet here, the ice becomes a detector, translating cosmic events into measurable light. The expansion of IceCube promises to capture even fainter signals, opening new windows into the violent births of stars, the collisions of black holes, and the deepest mysteries of particle physics. Each flash of light recorded is a whisper from the cosmos, telling a story that would otherwise remain silent, and demonstrating that Antarctica is not only a laboratory for biology, but a telescope for the universe itself. International collaboration shapes much of this work, as agencies such as NASA and ESA use Antarctic research stations as analogues for Martian exploration, habitats built on the ice test technologies for life support, energy efficiency, and robotic assistance. Scientists practice resource management, remote communication, and isolation strategies in conditions that simulate extraterrestrial settlement. Here, on Earth's coldest continent, humanity rehearses the practical and psychological challenges of inhabiting worlds beyond our own. The continent becomes a training ground for the cosmos, where every observation, experiment, and adaptation informs the next steps of exploration. Yet even as scientists probe these extremes, Antarctica faces unprecedented change. The slow creep of climate alteration threatens the stability of ice sheets, the composition of subglacial lakes, and the preservation of meteorites. Researchers speak of urgency, the need to document, sample, and understand the frozen continent before its pristine laboratories are irreversibly altered. In this tension lies a dual mission: preserving Earth's delicate systems while simultaneously preparing humanity for life among the stars. Every drill core, every sample, every telescope aimed skyward embodies this responsibility, intertwining planetary stewardship with the quest for cosmic knowledge. Modern Antarctic research thus spans multiple dimensions: biology, geology, climate science, astrophysics, and human endurance, each reinforcing the other. Microbial studies inform planetary protection protocols. Meteorite analyses guide models of cosmic exchange. Neutrino detection expands our understanding of the universe. Analogue missions sharpen strategies for interplanetary survival. In all of these efforts, the continent functions as a bridge, connecting the extremes of our planet to the vast possibilities beyond. It is both mirror and portal, showing what Earth has preserved and hinting at what awaits humanity in the cold, dark reaches of space. The stories emerging from these scientific efforts are quiet yet profound. They are tales of resilience and fragility, of hidden life and cosmic travelers, of human ingenuity tested in isolation. Antarctica is alive in these narratives, not through warmth or color, but through the weight of discovery, the clarity of thought, and the patience of researchers who move through its silence with purpose. The ice becomes a canvas for observation, the lakes a library of evolution, the meteorites a record of interplanetary journeys, and the night sky above a theater for fundamental physics. Each layer of study enriches the others, weaving a tapestry that positions Antarctica at the intersection of Earth and universe. In the quiet of the Antarctic night, under auroras that shimmer like distant galaxies, one senses that science here is both urgent and eternal. Every expedition is a rehearsal, every sample a message, and every discovery a step toward understanding life, the cosmos, and humanity's place between them. The continent's extremes demand respect, patience, and reflection, yet they reward those who endure with insights that resonate far beyond the ice. Antarctica is no longer just the edge of Earth, it is the threshold of exploration, a laboratory for survival, and a window onto the cosmos, offering a glimpse of what life can endure and what humanity may one day reach. In Antarctica, the pursuit of knowledge is a slow, deliberate dance with extremes. Drilling into subglacial lakes requires patience measured not in hours, but in the geological timescales encoded in the ice. Each centimeter pierced represents thousands of years of isolation, a world preserved beneath immense pressure and darkness. Researchers lower sterile sampling instruments into waters untouched for millennia, aware that even the smallest contamination could obscure the narrative written by evolution in solitude. In these hidden oceans, chemical gradients hint at microbial survival strategies, at energy flows sustained without sunlight, and at ecosystems that may mirror those beneath Europa's ice. Every analysis brings the tantalizing possibility that life is not only resilient, but versatile,